We introduced the Gaussian integers, z join I. The set of Gaussian integers we said is an integral domain. So that means they satisfy the zero product property. So we want to show that. It's a challenging thing to show, so proof. So we're going to take two arbitrary Gaussian integers, a plus ib, as well as c plus id. They're elements of the Gaussian integers. And we're going to assume that their product is 0. So let's suppose a plus ib times c plus id equals the 0 element, 0 plus I0. So the real trick here is to multiply, coming from the left, by the conjugate of a plus ib. So I'm going to take the conjugate of a plus ib, which is a minus ib, multiply on the left there. A plus ib, c plus id. And you do the same thing here, coming from the left. On the right side of the equation, a minus ib times 0 plus id, I0. So I don't know if you know this, but when you multiply these together, this is just the difference of squares, factorization. So the difference of squares here would correspond to, let's see, a squared minus I squared b squared. And then you have what? C plus id. And when you FOIL these out, you can FOIL these out if you like. You're going to have what? 0 plus I0 minus I0 minus I squared 0, which is just going to be, so this right here is all going to be just 0. Right, negative I squared is going to be just positive 1, so you're going to get 0 there. And when you add these together, or actually subtract these, you're going to get plus I0 there. Okay, and on the other side, do my double arrow. You're going to have a squared, and remember that this minus I squared right here, that's the same thing as plus 1, right? Because you have minus a negative 1. I squared is negative 1, so it's going to become a plus b squared. You got c plus id. Okay. In other words, this is equivalent to a squared plus b squared times c plus I a squared plus b squared times d. Right, we just multiplied a squared plus b squared through the integer part c and the imaginary part d. So we have this is equal to 0 plus I0. So here's our imaginary part in blue and our integer part here in red. This is all equivalent to saying that a squared plus b squared times c must be 0. And a squared plus b squared times d must be 0. Okay. So here we're at a very important step. So make a statement. Here's a fact. Note either a squared plus b squared, that has to be either 0 or not 0, or a squared plus b squared is not 0, right? A number is either 0 or it's not 0. So case 1. Let's pretend it is 0. That's this case right here. So case 1. Suppose a squared plus b squared is equal to 0. We're not going to go through the proof of why a and b will be 0, but I'm just going to state it. Then that forces a to be 0 and b to be 0. A and b must both be 0. So think if one of them is a negative, then a squared plus b squared will be positive. If one of them is a positive, then a squared plus b squared will be positive as well. So a and b both have to be 0. So what does that mean? That means then, in that case, a plus ib is going to be 0 plus I0. So that proves part of what we wanted to prove, that a plus ib could be 0. Well, case 2. Case 2. Let's suppose a squared plus b squared is not 0. Suppose a squared plus b squared is not 0. Now, if we go back to our equations here and here, and we use the zero product property on those equations, if a squared plus b squared is not 0, that forces c to be 0. So that means then c is 0 from this first equation in red. And then we go to the second equation in blue. If a squared plus b squared is not 0, that forces d to be 0. And that comes from the zero product property, so that means d must be 0. So that means c is 0 and d is 0, so therefore, then c plus id, well, if c is 0, we have 0 plus, and if d is 0, I0. So that proves the other part. What have we proven? The zero product property, right? We've proven that either a plus ib is 0, or c plus id is the 0 element. So we have shown that a plus ib is the 0 element, or c plus id is the 0 element. And that's it. That's the proof.